I'm a postdoc at the Technical University of Denmark, and I'll be talking about how we accidentally ended up with a Vulkan renderer. So the talk here will be about the stuff I did on my PhD, which started 3 years ago. And so there's some motivation which relates to my PhD and the research, and then some of the results that we achieved, and then some of the extensions that we used. I'll go a little bit into detail with those, but there are already great resources out there on how to sort of get the most out of those. So we're interested in visualization. We're really interested in sort of parts that come with visualization is inspection and interaction. So where we can scrutinize data and you can sort of have a communication either with a computer or with the data itself. With the computer, it would be like you ask the computer to give you a specific view of the data, and then you visualize it and look at it from that point of view. If you have the data in the real world, you can manipulate it and move it around. And we thought, hey, what about virtual reality, right? So being in the data gives a different perspective on the data. One example here is a 3D bar chart that you can look at, but if you were in that chart, I know it's not the most interesting type of data, but bear with me, it'll get more interesting. You can actually look down on some of the bars and up of the others, and you get a better sort of sense of scale. And this led us to investigate VR as a new way of handling these large data sets, because we get more and more data, and it becomes more and more difficult to sort of find the regions of interest that you would like to explore. And VR sort of allows you to do it in an intuitive way, where you can map your actual movement in the real world to the virtual world. You can zoom in just by moving closer to the data. But of course, it doesn't come without any challenges. And one of the challenges we have is that we need one render for each eye, right? So every time we render a frame, we need one view for the left eye and one view for the right eye. So there's a lot of performance constraints here. And these are sort of exacerbated by the fact that we need preferably around 90 frames per second. Otherwise, we risk that people get cyber sick, motion sick, or worst cases, throw up. That doesn't happen so often, but apparently it happens in rare cases. And in our specific case, we wanted to look at this scientific data. So we had and have still 12 different seal skulls that we have scanned and turned into 3D models. These range from 12.5 to 14.5 million triangles. And we have a PhD student that's really interested in figuring out whether this gray seal is one species or two subspecies. And the way she does that is to annotate the skulls and compare their shape. And we also have another mechanical department that do finite element modeling. And what they do is they do shape generation, like this wing, which is a Boeing wing that they have modeled. And they would really like to go into the finer details and inspect this structure to figure out which part they can actually manufacture in the real world and which part they need to maybe change to make it easier to do so. So we started out by going, great, we're interested in visualization. So we'll start by annotating skulls in VR. So what we did was we created a small program in Unity that we built where we put one of these skulls in, and then we wanted to compare that to a desktop solution and see if we were precise, more precise, less precise, if we could do it faster in VR. But it turns out that putting that skull into Unity completely throttled the frame rate. So we couldn't get good performance, so we couldn't do a good study. So what we ended up doing was decimating the mesh. So we actually, with a factor of 10, reduced the complexity of the mesh so that we can do the study. And I mean, this is not really a surprise, and it was quite naive of us to just throw this mesh in there and then assume that everything would just work. It wasn't until 2017 that Unity added a 32-bit index buffer solution. Before that, it was 16. So, of course, game engines are evolving to be these general-purpose tools, but they started with games, and in games you have low-res models, but a lot, and not one big one, right? So we were a bit naive, but this actually led us to most of what I did on my PhD, and now I'll present some of those results. And we started by saying, okay, what's a good place to start if we want to visualize large geometric data? We of course used Unity out of the box, like we did, which was the naive approach, and then we went a little bit deeper into Unity and optimized it, allowed it to do mesh optimization. So that's a little box you can check in Unity, and then it does some magic for you. You can disallow decimation, right? So you can say optimize the mesh, do what you will with the index buffer and whatever, but don't decimate the mesh. So that's of course what we did. And we then changed the pipeline. Now, when you open Unity today, you get a lot of different templates that you can pick that fit the need of your application. 3 years ago, this was a little bit less obvious, but we changed to the universal render pipeline, that many of you maybe know. And then we looked at the scientific community and we asked, what program do you guys use? And they use ParaView, which is quite often used for volume visualization and other aspects. It had a VR plugin. It doesn't allow for that much of more customization, so we just used that out of the box. And then we made 2 very simple Vulkan renderers. We made one using the vertex shading pipeline and one using the mesh shading pipeline. And I won't go too much into mesh shading because I know tomorrow we'll have a great talk on how to use it properly. So I just hope that I'm somewhat in line with some of the best practices that will be taught tomorrow. But essentially, instead of processing a mesh at the granularity of vertices, you do it at meshlets. And meshlets is small clusters of vertices and triangles. And what's really cool with this is that you have a task shader before you process the meshlet, and that task shader can look at the bounding box of a little cluster, and it can say, okay, this cluster is actually not visible, so let's not process all the triangles and the vertices, right? And that's super great, especially for our use case, because we're in VR, and I wanted to inspect data, and that is scrutinizing it. So we typically get up close, right? So we're setting up an experiment where we have a good chance of seeing some really great improvements by being up close to the mesh and culling large parts of it. Okay, so here's the initial comparison, and we had 2 test studies. We had one where we looked at the mesh from far away to get an overview of the mesh, and then we had one where we looked at it up close. So the crosshatch bar is looking at the mesh up close, and the nuthatch is looking at from afar. We have the average render time on the y-axis. 11.1 milliseconds is the 90 frames per second. That's the gold standard that we want to hit. And what we can see here is that, like we experienced, Unity didn't do well, but once we optimize Unity does quite well, right? And actually does the best. And we don't see any benefit yet from the mesh shading pipeline, despite being up close. So, but we're around 3-4 milliseconds per frame, so we're not really expecting to see that much. But that changes a bit when we go into the wing, right? So when we inspect larger geometric meshes, we start seeing the mesh shading pipeline do better, especially compared to Unity. We beat Unity. I would say we're on par when we look at it far away, and when we look at it up close, we're actually twice as fast as Unity. So, and of course, you know, this isn't like you shouldn't do Unity, you should do your own engine all the time, kind of, but Unity is a big monster, right? It does a lot of things. I just want to visualize a mesh. So that's a small part of what Unity does, and I, of course, can optimize towards that a little bit better than Unity can, because Unity is juggling all kinds of other things that is useful for a lot of other users, right? But we can actually go further, because this was just using a Vulkan engine based on all the tutorials and that you can find online, but you can also use other features and extensions to improve performance even further. So we can use multi-view extensions, we can use variable rate shading, and we can also look a little bit at the meshlet clustering. And this again improves our performance. So with the multi-view, we actually shave off 2 milliseconds in both looking at the mesh from far away and up close. We don't really see a big change with variable rate shading. That's because we have a simple shader. So we're not fragment bound, as we learned yesterday. That's when this helps. We're geometry bound. And then we changed the meshlet clustering from a very naive approach to something that's still greedy and still fast, but a little bit better. Now I want to briefly cover some of these extensions as the last part of the talk. So with the multi-view extension, instead of having the view for the left eye and the right eye be processed one at a time, we can extend, or we can use this extension to just have one task shader and mesh shader evocation, and then 2 fragment passes, one for each eye. And this works really well when you have 2 views that are looking at roughly the same geometry, because then you can sort of reuse the geometry and don't have to load it in over 2 passes. And there's a paper out, so I'll plug Unser Guggenberger and Kerbal, again, they have a paper on this. So if you want to look more into how you can tweak this, look at their paper. It's called Fast Multi-View Rendering for Real-Time Applications. But setting it up is fairly simple. We just, at the render pass creation, we extend the render pass create info struct with a render pass multi-view create info. And that has a correlation mask and a view mask that we set up. So we say we want to render these two images next to each other and they correlate highly. And then we create a frame buffer image attachment with the corresponding number of layers as we have views. You can do this with more views as well. It goes up to, I think, 16 views, and 8 of these can be in hardware, and the rest will then be done differently. But in our case, 2 was enough. And then in the shader, you enable the GL-NVX multi-view per view attributes extension. And that gives you a view count, right? So you can use this to go through the number of views. You can hard code this in if you know that, okay, I have 2 views, but you can also be more dynamic and go through that. And you can use the view index in the GL mesh view indices struct to get an index out that you can use for your mesh array to change the positions. And you even get a per view NV prefix that you can add to your own structs, so you know you can output these per view if you want to. The other thing we got a very detailed and very great talk about yesterday is the variable rate shading. And that was a much more involved example. I'm using it for VR. I don't have eye tracking, but I simply set up an image where the fovea, and I think there were some questions about it yesterday, but you know, if you do this in VR, then it looks it looks acceptable compared to these images where you can see like the fall off in the fragment calls per pixel. But the fovea is where you want the one fragment call per pixel, and then as you move out into the periphery of the eye, you can reduce this. And again, if you have a sort of, and this was actually done with the NVIDIA extension. So once again, I'm sorry that there's a trend here in the in the scientific, the unofficial scientific blog that we all use NVIDIA cards, and it's, yeah, it may reflect all a lot of research, it may not, but I also used NVIDIA and used the NVIDIA extension for this, and that means that I can set up the image usage with a new bit, and then I can use this palette that NVIDIA provides when you use this extension to fill up an image and copy it to the GPU, similar as to what was done yesterday. And then you can extend your viewport create info structure with a shading rate create info structure that tells your pipeline what entries from the palette you used. And when you then start command buffer recording, you can find your new image and render to that, right? So there's small changes here and there, but once you have your general Vulkan application up and running, it's actually just little bits here and there that you change, and then these extensions work quite well. All right, so the last thing we did was we changed the meshlet clustering algorithm, and we start by generating 2 data structures, one for the triangles and one for the vertices. And each triangle knows its neighbors, and that's just all the triangles that it shares an edge with. And each vertex knows all the triangles that it's part of. And this allows us to quite quickly look at the border of a meshlet once we go further down. And another thing we did was we sorted the vertices. So essentially, once we have our vertex list, we sort it along the longest bounding box axis, because then we find that we sort of gradually fill up with vertices rather than start some random point and grow out. Because if we do this, then we found that we ended up with small islands of triangles here and there that is in the end have to either be in meshlets that are not fully filled, or fully filled but then fragmented all over your mesh, and that gives them a big bounding box. And when you have a big bounding box, it's hard to call them. All right. So what we did was once we've sorted the vertex list, we ran through the list, and then we started from the first vertex in that list, and then we grew our meshlet from there. And we grow them in a way where we try to minimize a bounding sphere. So we have a radius attached to the meshlet that grows every time you add a new meshlet. And we look at the bounding, what's it called? The edge of the meshlet for all the triangles that are there. We go through those triangles and find the one that minimizes it, right? So that's why we need the two structures to constantly keep track of the edge of our meshlet. Once it's full, we found that we more often than not hit the vertex limit than we hit the triangle limit. So the vertex limit, we used NVIDIA's recommendation, which is 40 or 64 vertices per meshlet and 124 triangles. And we would much more often hit the 64 vertex limit before hitting the triangle limit. So we could look at the boundary and maybe add an extra vertex or triangle for free because all the vertices were already in the meshlet. And then we started over, right? So I think the takeaway from this presentation is that we compared it to Unity 3 years ago. Now we would have to compare it to Unreal 5 and their VR nanite system. This might be a different story, but it took Unreal 4 years from we actually got the hardware to actually give this to developers. So Vulkan is a really great way of getting access to these extensions and also vendor-specific extensions before they become Vulkan Core or before they become incorporated into the software that you want to use. Yeah, and that was it. Thank you. Any questions? Yeah.
So,
yeah.
I wanted to ask, are you considering porting your application vendor?
Yes, I would definitely consider doing that for both the variable rate shading and the mesh shading. That definitely makes sense to do.
So is this available somewhere?
So this I made the mistake of asking our HR department if I could put this on GitHub. Rookie mistake, I tell you, because they were not happy. So I'm in the process of figuring that out, and then it will be available on my GitHub. Yeah, I guess I'll put a comment. I'll send you an email because your email is somewhere on a slide tomorrow for the lecture probably, and then I don't know, maybe not. Or I'll put. Yeah, exactly. Yeah, that's.
Two questions.
Okay.
First one is, with such obnoxious amounts of triangles, did you consider going with ray tracing or just abandoning triangles anyway because they're going to be sub-pixel and developing like a point cloud renderer instead?
We considered ray tracing, and we also looked at it back. So 3 years ago, we also saw that, of course, the cool thing about ray tracing, which is sort of in between the lines of the question, is that it's not triangle bound. So you get some. So that's really nice. But we're in VR, and we can't really hit the frame rate with ray tracing right now. We looked at a graph back when the Turing architecture came out 3 years ago, and saw that your frame rate, your frames per second, sort of increases more slowly with the size of the mesh when you use ray tracing than when you use rasterization. But we couldn't decimate the meshes, right? So we were stuck with achieving 90 frames per second or 180 frames per second, because we need one for each eye, for VR without touching the mesh. Because if we start decimating the meshes, what's the point of what's the point of inspecting the mesh then, right? Because we're in a scientific setting. If we were in a game setting, then things might be different. Or if the actual structure of the mesh wasn't important, we could do other things. Point cloud could be interesting. Actually, when we scan the skulls, they are point clouds, and then we turn them into 3D. So that could be interesting, but it makes it hard to annotate a point cloud if you want to annotate a surface, right? So these explicit surfaces are important for the shape morphology study, because you want to annotate that surface. Follow-up question.
Yeah, so with stuff like diligence, filaments, so on and so on and so on, why did you not start off from those or fork those to get your whole?
That's a good question. Yes. So the question is, why did I build my own engine and not start from other existing engines? And I think it was a matter of being in the cave, in Plato's cave analogy. So I wasn't aware of this ecosystem when I started out on my PhD. I didn't do a lot of graphics before that. I was interested in the visualization aspect. So I found the vulkantutorial.com, and that had a way of doing things, and that's where I started. And then I had this main file with 1,000 lines of code that I was refactoring, and I think over and over, and I still today, when you do stuff, it's like, oh, I should have done it differently. But it takes, you know. So could I start over today? Then I would probably do it differently. But I also feel that my attempt at an engine is very specific in what it does. So a lot of these nice to have things and things that really help you in dynamic settings where you load and unload meshes and textures and things. I didn't sort of experience those pains, which would probably have put me on the path of using other frameworks, if that makes sense. All right. Thank you once again for listening.